Welcome to the sessions on food technology. We are discussing on trickling filters. Trickling filters are also called as trickling biofilter, biological filter and biological trickling filter, which are generally used to remove organic matter from wastewater. The trickling filter is a fixed bed biological reactor that operates under aerobic conditions that utilizes microorganisms attached to packing materials such as rock, gravel, slag, sand, redwood and a wide range of plastic and other synthetic materials to remove organic matter from wastewater. This type of system is common to a number of technologies such as rotating biological contactors and packed bed reactors. These systems are known as attached growth processes where pre-settled wastewater is continuously trickled or sprayed over the filter. In contrast, systems in which microorganisms are sustained in a liquid are known as suspended growth processes. The trickling filter is one of the most common attached cell processes. Unlike the activated sludge and aerated lagoon processes which have biomass in suspension, most of the biomass in trickling filters are attached to certain support media over which they grow. Trickling filter is considered as a best method for wastewater treatment. In this episode, we are going to understand the trickling filter process under the following topics. The first is design criteria of the trickling filter, what are the process description, microbiology of the trickling filter, types of the filters and operation and maintenance of the trickling filter, advantages and disadvantages of the method. Let us understand the design criteria. Trickling filter consists of a permeable medium made up of a bed or a rock or slag or plastic over which wastewater is distributed to trickle through. Rock or slag beds can be up to 60.96 meters in diameter and 0.9 to 2.4 meters deep with rock size varying from 2.5 to 10.2 centimeter. Most rock media provides approximately 149 meter square to meter cube of surface area and less than 40% void space. Packed plastic filters, they are also called as biotowers, on the other hand are smaller in diameter which varies from 6 to 12 meters and range in depth from 4.3 to 12.2 meters. These filters look more like towers with the media in various configurations, example vertical flow, cross flow or various random packings. Research has shown that cross flow media may offer better flow distribution than other media, especially at low organic loads. When comparing vertical media with 60-degree cross flow media, the vertical media provide a nearly equal distribution of wastewater, minimizing potential plugging. The design of the trickling filter system of wastewater also includes a distribution system. Rotary hydraulic distribution is usually standard for this process, but fixed nozzle distributors are also being used in square or in rectangle reactors. However, fixed nozzle distributors are being limited to small facilities and package plants. Recently, some distributors have been equipped with motorized units to control their speed. Distributors can be set up to the mechanically driven at all times or during stalled conditions. In addition, a trickling filter has an under-drain system that collects the filtrate and solids and also serves as a source of air for the microorganisms on the filter. The treated wastewater and solids are piped to a settling tank where the solids are separated. Usually, part of the liquid from the settling chamber is recirculated to improve wetting and flushing of the filter medium, optimizing the process and increasing the removal rate. It is essential that sufficient air be available for the successful operation of the trickling filter. It has been found that to supply air to the system, natural draft and wind forces are usually sufficient if large enough ventilation ports are available or provided at the bottom of the filter and the medium has enough void area. The following four basic categories of filter design are based on the organic loading of the trickling filter. The trickling filters also require the primary treatment for removal of settleable solids and oil and grease to reduce the organic load and prevent the system of blocking. Rock or blast furnace slag have traditionally been used as filter media for low rate and intermediate rate trickling filters, while high rate filters tend to use specifically fabricated plastic media, either as a loose fill or as a corrugated prefabricated module. The advantage of trickling filter is their low energy requirement, but the disadvantage is the low loading compared to activated sludge, making the plant larger with a consequent higher capital cost. The overall BOD removal efficiency can be as great as 95%, but this is dependent on the loading applied and the mode of operation. Generally, trickling filter design is based on empirical relationships to find the required filter volume for the design degree of wastewater treatment. There are different types of equations employed in the process, such as NRC equation, National Research Council of USA, Rankin's equations, Eckenfelder equation, and Galler and Gotta's equation, out of which the first two reactions are widely used. NRC equation results in highly satisfactory values when there is no recirculation, the seasonal variations in temperature are not large, and fluctuations with high organic loading is not seen. Rankin's equation is used for high rate filters. So, let us see what is NRC equations. These equations are applicable to both low rate and high rate filters. The efficiency of single stage or first stage of two stage filters E2 is equal to 100 divided by 1 plus 0.44 multiplied with F1 point BOD divided by V1 RF1 to the level of half. For the second stage filter, the efficiency E3 is given by E3 is equal to 100 divided by 1 plus 0.44 divided by 1 minus E2 F2 dot BOD divided by V2 RF2 to the power of half. This can be seen in the screen, where the E2 is equal to percentage efficiency in BOD removal of single stage or first stage of two stage filter. E3 is equal to percentage efficiency of second stage filter. F1 BOD is equal to BOD loading of settled raw sewage in single stage of the two stage filter in kilogram per day. F2 BOD is equal to F1 BOD, that is 1 minus E2 is equal to BOD loading on second stage filter in kg per day. V1 is equal to volume of first stage filter in meter cube. V2 is equal to volume of the second stage filter in meter cube. RF1 is equal to recirculation factor for first stage. R1 is equal to recirculation ratio for first stage filter. RF2 is equal to recirculation factor for second stage. R2 is equal to recirculation ratio for second stage filter. So, what is Rankin's equation speaks of? This equation, also known as tentative method for 10 states. USA has been successfully used this equation over wide range of temperature. It requires following conditions to be observed for single stage filters. The first one being, the raw settled domestic sewage BOD applied to filters should not exceed 1.2 kg BOD per day per meter cube filter volume. The second one, hydraulic load, which includes the recirculation, should not exceed 30 meter cube per meter square filter surface per day. The third one being recirculation ratio, that is R by Q, should be such that BOD entering the filter, including the recirculation, is not more than 3 times the BOD expected in the effluent. This implies that as long as the above conditions are satisfied, efficiency is only a function of recirculation, and it is given by E is equal to R by Q plus 1 divided by R by Q plus 1.5. In order to achieve optimum operation, several design criteria for trickling filters must follow the following criteria. The first one, the roughing filters may be loaded at the rate of 4.8 kg BOD per day per meter cube filter media and achieve BOD reductions of 40 to 50%. High rate filters achieve BOD reduction of 40 to 70% at organic loadings of 4.8 kg per BOD per day per meter cube. And the last one being, the standard rate filters are loaded at 0.08 to 0.4 kg per BOD per day per meter cube and to achieve BOD removal greater than 70%. With regard to the packing over which the biomass grows, the void fraction and the specific surface area are important features. The first is necessary to ensure a good circulation of air, and the second is to accommodate as much biomass as possible to degrade the organic load of the wastewaters. Although more costly initially, synthetic packagings have a large void surface, larger specific area, and are lighter than other packing media. Usually the air circulates naturally, but forced ventilation is used with some high strength wastewaters. The latter may be used with or without recirculation of liquid after the settling tank. The need for recirculation is dictated by the strength of the wastewater and the rate of oxygen transfer to the biomass. Typically, recirculation is used when the BOD of the seafood processing wastewater to be treated exceeds 500 mg per liter. The BOD removal efficiency varies with the organic load imposed, but usually fluctuates between 45 and 70% for a single stage filter. Removal efficiencies of up to 90% can be achieved in 2 stages. So, let us go to the second topic that deals with the process description. The following steps were observed in trickling filter process. The wastewater in the trickling filter is distributed over top area of vessel containing non-submerged packing material. Air circulation in the void space by either natural draft or blowers provides oxygen for the microorganisms growing as attached biofilm. During operation, the organic material present in the wastewater is metabolized by the biomass attached to the media. The biological slime grows in the thickness as the organic matter abstracted from the flowing wastewater is synthesized into the new cellular material. The thickness of the aerobic layer is limited by the depth of the penetration of oxygen into the microbial layer. The microorganism near the medium phase enter the endogenous phase as the substrate is metabolized as a result of increased thickness of the slime layer and lose their ability to cling to the media surface. The liquid then washes the slime off the medium and a new slime layer starts to grow. This phenomenon of losing the slime layer is called as sloughing. The next process is the sloughed off film and treated wastewater are collected by an under drainage which also allows circulation of air through filter. The collected liquid is passed to a settling tank used for solid liquid separation. Excess growths of microorganisms wash from the rock media and would cause undesirably high levels of suspended solids in the plant effluent if not removed. Thus, the flow from the filter is passed through a sedimentation basin to allow these solids to settle down. This sedimentation basin is referred to as the secondary clarifier or final clarifier to differentiate it from the sedimentation basin used for the primary settling. An important element in trickling filter design is the provision for return of a portion of the effluent, that is recirculation, to flow through the filter. Trickling filter enable organic material in the wastewater to be adsorbed by the population of microorganisms, which may include aerobic, anaerobic, facultative bacteria, which may also include fungi, algae and protozoa attached to the medium as a biological film or slime layer, and its size may vary from 0.1 to 0.2 millimeter in thickness. As the wastewater flows over the medium, microorganisms already in the water gradually attach themselves to the rock, slag or plastic surface and form a film. The organic material is then degraded by the aerobic microorganisms in the outer part of the slime layer. As the layer thickens through microbial growth, oxygen cannot penetrate the medium phase and anaerobic organism develops. As the biological film continues to grow, the microorganism near the surface lose their ability to cling to the medium and a portion of the slime layer falls off the filter. This process is known as already mentioned sloughing. The sloughed solids are picked up by the under drain system and transported to the clarifier for removal from the wastewater. Overall, trickling filter involves the aerobic conversion of the waste and it is summarized as follows. That is, organic waste in presence of oxygen gets converted into the cells plus carbon dioxide and water, and carbon dioxide being volatile compound enters the environment and water mixes with the wastewater. Third topic that we are understanding today is the microbiology of the trickling filter. Two types of microorganisms live in waters. suspended organisms floating in the water, and sessile organisms which often settle on the surface of the stones and form biofilms. Biofilm processes such as fixed bed or trickling filter processes are examples of the technical application of these natural processes. Typical microorganisms present in the trickling filters are Zuglia, Pseudomonas, alkali genes, Flavobacterium, Streptomyces, Nocardia, fungi and protozoa. The crux of the process is that the organic contents of the effluents are degraded by these attached growing populations which absorb the organic contents from the surrounding water film. Oxygen from the air diffuses through this liquid film and enters the biomass. As the organic matter grows, the biomass layer thickens and some of its inner portion become deprived of oxygen or nutrients and separate from the support media, over which a new layer will start to grow. The separation of biomass occurs in relatively large flocks that settle relatively quickly in the supporting material. Media that can be used as rocks or plastic structures. Denitrification can occur in low rate filters while nitrification occurs at high rate filtration conditions. Therefore, effluent recycle may be necessary in high rate filters. The fourth topic is going to be the type of filters and operation and maintenance. Trickling filters are classified as high rate or low rate based on the organic and hydraulic loading applied to the unit. The hydraulic loading rate is the total flow including recirculation applied on the unit area of the filter in a day, while the organic loading rate is the 5-day 20 degree centigrade BOD, excluding the BOD of the recirculant applied per unit volume in a day. Recirculation is generally not adapted in low rate filters. A well operated low rate trickling filter in combination with secondary settling tank may remove 75 to 90% BOD and produce highly nitrified effluent. It is suitable for treatment of flow to medium strength domestic wastewaters. The high rate trickling filter, single stage or two stage, are recommended for medium to relatively high strength domestic and industrial wastewater. The BOD removal efficiency is around 75 to 90%, but the effluent is only partially nitrified. In single stage unit consists of a primary settling tank, filter, secondary settling tank and facilities for recirculation of the effluent. Two stage filters consist of two filters in series with a primary settling tank, an intermediate settling tank which may be omitted in certain cases and a final settling tank. The efficiency of different filters can be assessed through its ability to reduce BOD of the waste. It is estimated that low rate filters remove BOD up to 80 to 90%, intermediate rate filters up to 50 to 70%, whereas the high rate filters is up to 65 to 80% and roughing filters are known to remove up to 40 to 65%. So, what is the operation and maintenance we have to follow for the trickling filter? The first component that seems to be for maintenance component is disagreeable odors from filter. So, what could be the cause? Excessive organic load causing anaerobic decomposition in the filter. So, what should be the remedy for it? Reduce the loading, increase BOD removal in primary settling tanks, enhance aerobic conditions in the treatment units by adding chemical oxidants, pre-aeration, recycling plant effluent or increasing air to aerated grid chambers, scrub off gases, use plastic media instead of rock. The second potential cause is the inadequate ventilation. The remedy for this is increase hydraulic loading to wash out excess biological growth, remove debris from filter effluent channels, under drains and the top of filter media, unclog vent pipes, reduce hydraulic loading if under drains are flooded, install fans to induce draft through filter, check for filter plugging resulting from breakdown of the media, and along with this several other factors such as ponding on the filter media, icing, rotating distributor slows down or stops need to be considered while operating the trickling filter. So, let us understand the final topic, the advantages and disadvantages of the method. Even though trickling filter is considered to be the best method employed in wastewater treatment, it has both advantages and disadvantages. Let us see what are the advantages. It is very simple, reliable, biological process. It is suitable in areas where the large tracts of land are not available for land intensive treatment systems. It qualifies for equivalent secondary discharge standards. It is effective in treating high concentration of the organics depending on the type of the medium used. It is appropriate for small to medium sized communities. It rapidly reduces soluble BOD in applied wastewater. It is a efficient nitrification units. It requires low power, moderate level of skill and technical expertise is needed to manage and operate the system. Because of the relatively high strength of the slaughterhouse wastewater, biological filters are more suited for operation with effluent recirculation, which effectively increases surface hydraulic loading without increasing the organic loading. So, this gives greater control over microbial film thickness. The another one is the for mill wastewater having high BOD of BOD. So, that is from 4075 milligram per liter, trickling filter is the best option. So, let us see what are the disadvantages of the trickling filter. Additional treatment may be needed to meet more stringent discharge standards. Possible accumulation of excess biomass that cannot retain an anaerobic condition and can impair trickling filter performance. And for example, maximum biomass thickness is controlled by hydraulic dosage rate, type of media, type of organic matter, temperature and nature of the biological growth that need to be stringently regulated. It requires regular operator attention. Incidence of clogging is relatively high and if neglected may impart bad odor. Requires low loading depending on the medium. Its flexibility and control are limited in comparison with activated sludge processes. There is a problem of vector and odor. There is a problem of snail. An inherent problem is that trickling filters can be blocked by precipitated ferric hydroxide and carbonates with concomitant reduction of microbial activity. In the case of overloading with dairy wastewater, the medium becomes blocked with heavy biological and fat films. Biological filters are not appropriate for the treatment of high strength wastewaters, as filter blinding by organic deposition on the filter medium is generally bound. So, conclusion of today's discussion is that for treatment of industrial wastewater, trickling filters are often used as a popular biological treatment process. The most widely used design for many years was simply a bed of stones having 1 to 3 meter depth through which the wastewater passed through. The wastewater is typically distributed over a surface of the rocks by a rotating arm. Rock filter diameters may range from 60 meter. As wastewater trickles through the bed, a microbial growth establishes itself on the surface of the stone or packing in a fixed film. The wastewater passes over a stationary microbial population, providing contact between the microorganisms and the organics. The biomass is supplied with oxygen using outside air, most of the time without additional technical measures. It is not surprising that BOD can be reduced to the extent of 90%. Due to microbial positive and negative interactions in the biofilm, it is also possible to reduce the pathogenic microbial load, even including viruses. Each rock particle represents a microcosm where several activities led by microbial world cleans the waste from industrial effluents. If properly managed, it is the best method for wastewater treatment. Thank you.